Yeah. So yeah, the idea that I was trying to get across is that in the effective field theory, the heavy particles are integrated out. So they effectively have a mass which is like infinity. And because of this, when you have a log in the full theory that would have been in a ratio of a light mass over a heavy mass, which is integrated out in the effective field theory, this appears like a divergence. And this fact that they appear like UV divergences means that you can apply the techniques we have for solving renormalization group equations that we have in the field theory as well. And we can, and by solving the renormalization equations, then we can effectively resum the logs. Does that make sense? Or maybe you can ask me another question.
So, like, if we wanted to do the same thing, like the resummation in the full theory, we need to take the heavy field as well, and like for that there will be. So how it will be different in calculation?
Yeah, how would you resum it in the heavy, in the full theory? The only way you can resum it in the full theory is by calculating all the diagrams.
Yeah, so all the diagram in the same order.
No,
Or you mean
to infinite order.
Okay, I see.
Yeah.
Yeah. Thanks.
Okay, great. Any other questions?
Does the calculation of the Wilson coefficients depend on the external momenta of the quarks that we consider initially?
No, luckily not. No. So all of the information about the momenta of the quarks is in the operators, and the Wilson coefficients are just simply numbers depending on masses and the scale mu.
So for matching, we can choose any particular value of the external momenta of the quarks.
Yeah. So you can choose whatever makes the matching simplest.
And what about their masses? Should we take the masses of the external quarks to the physical masses only, or we have a freedom there also?
No, no, you should keep them physical values. Yeah.
Okay.
Any more questions?
So, so Wilson coefficient depends on the scale, and operators also depends on the scale. So, does it cancel fully, or it remains after
they can
also?
No, they have to cancel fully the scale dependence of the Wilson coefficient and the operator, and the Green's function. Yeah.
Okay, but I have read that for every case they don't cancel.
Sorry?
For different cases, like for one case I have read that the scale does not cancel and it leads to theoretical uncertainty. Something like that.
Okay. Yeah, no, it's a good question, and it's true that when we calculate, so the Wilson coefficient and the operators can't scale dependence cancel, but it's true that when you calculate the a process, there might be some remaining scale dependence because and this is indeed because we don't go to all orders.
So
In order for me to explain that, maybe I need to think a little bit. So maybe I should tell you about that tomorrow.
is it because we truncate the series at certain order?
Oh
then-
yeah, that's definitely true. But even order for order, the Wilson coefficients and the operator scale dependence will cancel.
Okay.
And if you're if you are doing resummation of all the orders, then
Yeah, because you only resum the leading log term
yeah, you're doing that only.
or the next leading log term. Yeah. We're not resumming we're not obtaining the result at infinite order in perturbation theory. We're just obtaining the result of the leading log term at infinite order or the next leading log term at infinite order. So there'll be other suppressed log terms and other finite terms, which are, terms that are not dependent on logs, which will not be resummed.
Yeah, but I was thinking that, yeah, it's the same way at every order. Like if I'm doing at NLO, so I'm taking operator and Wilson coefficient both at NLO. So, and doing resummation. So why should it not be cancelled at that order? I don't know.
Okay, but when you calculate a process, it's more complicated than just the Wilson coefficient and the operator. So the scale dependence can come in different places. Let me think about this and give you a concrete example, and I'll discuss that tomorrow.
Okay, thank you.
Okay. I think it's easier if we look at a concrete example. Okay, any more questions? Okay, so yeah, today I wanted to talk, in this lecture 3, I wanted to talk a little bit about the form factors. But before we get there, I'd like to talk just a little bit about calculating exclusive processes in general. So if we think about some exclusive decay of a B meson, we have we have the Quark decay. So let's take an example. To start with, we'll take a simpler example, which would be a semi-electronic decay of the B to electron neutrino. This could be U, it could be C. Let's say it's U. Okay, so we have a B quark decaying to a U quark, an electron neutrino. And do you know why? And why would we look at this process? Why do we want to measure this quark decay? I'm sure you know. What is present in this vertex?
VUB.
Yeah,
VUB.
yeah. So to measure VUB. Okay, thank you. Yeah. So, okay, so we want to measure this process in order to get access to VUB. But the problem is that this quark decay does not appear in nature by itself, and the B meson will always be part of some baryon or meson. So let's take the example of the meson because it's simpler. So we have something called a spectator quark here. So this could be a D, for example, or a U bar, let's say. No, no. let's make it a bit simpler and more standard. Okay, so we have a D bar and a D bar. So here we have a charged pion, and here we have a neutral B meson. Okay. So in order to calculate, we can easily calculate the partonic part of this process. So that means the quark decay into the lepton neutrino. But how do we calculate the mesonic decay? So in this case, it's actually not so complicated, and you can describe this whole part in terms of, what does someone know? What parameterizes the part that I circled? Yeah?
Form factor.
Yeah, right. So the beta pi form factor provides the non-perturbative information. Okay. So now we know that the best way to study this process is via a form factor. Initially, the very first papers on the subject thought that in the same way as you do in for the pion and also for proton decays, that you could just describe the B separately in terms of its light current distribution amplitude. And then, oh, this is wrong. And use the LCD for the pi to describe the pion. And this part was described by something called the Heart Kernel. And they were thinking that by convoluting these three things, so you have the B meson light current distribution amplitude, the Heart Kernel, and the phi pi, the pi meson light current distribution amplitude, you could describe this process. But it turns out that this contribution, which is called the Heart
Sorry,
Kernel,
can you explain a little bit about LCD and light current distribution amplitude?
Yeah, sorry. Yeah. I was about to. No, you're right. I was going too fast. So what is this LCD? It's quite simple. So it's an object which depends on U, which is the momentum fraction of one of the quark constituents. So you have, imagine if you have a B meson with momentum PB, and this, at the leading order, it contains just the B and the D bar, and these could have momentum fractions U and 1 minus U. So the momentums would be UPB and 1 minus UPB. So phi is a function that describes the probability that the B meson will have momentum fraction U and the D bar a momentum fraction 1 minus U. That's it. So it's quite simple. And it's the same for the pion. So it's just it's a bit like the PDF of the proton. It gives you some information about the fraction of momenta of the constituents. Okay, is that clear?
Okay. So are we considering here gluon as soft? So
In respect to what?
because if you're considering B meson, so we are taking the fraction of momentum of this B quark and the D quark. So what about the gluons? Which are
Yeah,
present in
exactly. Yeah, no. So I only presented something called the twist 2 light cone distribution amplitude. So in the twist 2, it's the leading one. And in this leading one, there's only 2 constituent partons. Then you can have higher order light cone distribution amplitudes, which take into account gluons. Okay. Okay. So as I was saying, at first people thought you could calculate it like this, and then they realized that in fact, this configuration does not take into account the largest contribution, which can only be described if one takes into account a non-perturbative object which describes the initial and the final state. And this is called the form factor. Okay, so however, okay, that's enough.
Excuse me, ma'am. Can you
Yeah.
repeat what are the form factor?
So the form factor, I'm going to define it in a moment, but the form factor are non-perturbative objects which describe how this quark transition fits into the meson transition. Okay, so maybe I'll define it right now. So for example, for a B meson going to a pseudoscalar meson, so we call it K, the P, the pseudoscalar meson. And you can have some quark current. This could be different. This is just one example. And then you have some kinematics. Okay, so this expression, so here we have a vector current between some B quark and some light quark. This can be expressed in terms of 2 form factors, F plus and F0. And it turns out that in order to get VUB, all we need to know is F plus. So the decay rate can be written in the limit of massless electrons entirely in terms of F plus. So therefore, in order to compare with the experiment, all we need to know is this form factor, which we have to calculate using non-perturbative techniques. Does this answer your question? So Q mu is P minus K. So for beta pseudoscalar transitions, there's 3 form factors. So we can either have the vector current, or if we have the tensor current, then we get an additional form factor, which is called FT. So there's 3 form factors, F plus, F0, and FT. I'm not going to write down all the definitions because it will take too long to write down, but I can give you a reference. And there's 7 form factors for B to V decays. So there's a vector form factor, so A0 to 3 and T1 to 3. And I've written down 8, but there's only 7 independent because you can rewrite A3 in terms of A1 and A2. Okay. So so now what I wanted to do was to show you very simple to sketch, a simple calculation of the like-term sum rule for F plus, which is, as I mentioned, the only form factor that's necessary in order to get VUB. Okay. Does anyone have any questions before? Okay. So it's not very complicated. Okay, so the first thing one does when we want to obtain a like-term sum rule is we write down a correlator, which we choose because it's going to be a form that's going to be useful. So we call this correlator pi mu. That could be as a, yeah.
So Aoife, there was a question in the chat actually.
Yeah, how we determine number of form factor in BTP transition. Good question. I actually never thought about that, how to know the number of form factors. But I guess it's connected to the number of degrees of freedom. In the end, one has to write out the most general combination of these different 4 vectors and see how many coefficients we need. But there's one slightly easier way to think about it. Just hold on a second. So we can either write down the I'm looking into my thesis. Yeah, I mean, it's related to the polarization vector of the vector meson, which allows more degrees of freedom in writing down possible coefficients for the form factors. But yeah, it's not a very satisfactory answer. Maybe I'll think about it and come back to you. I'll write a list of questions that I need to answer tomorrow. Okay, so coming back to the calculation of this correlator. So we make a time ordered product of this current from B to U at 0, and then B to D at position X. And with the vacuum outside. So, okay, so we have this product of currents inside a correlator going from the vacuum to the pion. Then again, you can write this down in terms of 2 scalars because it's a vector which we call pi plus, which corresponds to the F plus form factor, and pi minus. Okay, so looking at the form of this correlator, we notice that if we want to represent this correlator in terms of hadronic contributions, we could see that it's dominated by, at low Q spread, by the B meson. Okay, so we can write down, now we're writing it down for pi plus. So supposing we, when we're around close to this B meson pole, it takes this form, because imagine if we insert a B here, a B here, then on the left, we have the definition of the form factor. And on the right, we have the definition of FB, the B meson decay constant, which is defined like this. NB squared FB equals NB 0 B I gamma 5 B B. Okay, so you can clearly see that if we insert this here, we get FB, and if we insert this F plus here, this, you can see it's the same thing, then we get F plus. Okay, so in the end, we get something that looks like this. And then when we go to higher momenta, we can write it as in terms of a spectral density with hadronic states, where S is greater than NB squared. Okay, so we call this the hadronic representation of the correlator. Now, alternatively, we can go to the Euclidean region . Where MB B square minus MB square is large and negative. We can Lycon expand around x bar equals 0. So here, for the correlator, we get a sum over some perturbatively calculated Heart kernels labeled by increasing twist. But twist is what I said was labeling these Lycon distribution amplitudes. And this U again is the fraction of momenta. So this is the pion Lycon distribution amplitude. So there's an alternate, yeah?
Ma'am, what do you mean by Heart kernel?
Yeah, it's just some coefficient which can be, so we're doing something like a factorization where we put the non-perturbative stuff into the Lycon distribution amplitude, and we put the perturbative stuff into this quantity called what we just call the Heart kernel. It's called the Heart kernel because it contains the heart of physics, where the soft part is in the Lycon distribution amplitude. And this can be calculated perturbatively. Okay. So I'll show you in a minute a little bit about how one could calculate. So, not really, but okay. Yeah, I'll show you slides here. So, I mean, at leading order, this thing is just very simple. Okay. So at leading twist and leading order, so leading order in alpha S and leading twist. This pi plus can simply be calculated to give f pi and v squared over 2 u pi v squared over v squared minus v squared minus v bar v squared. So you get this expression. I'm not gonna calculate it here, but by doing something like this, okay, so okay, so these combine to give the pion. I'm just gonna check before I say something else. Yeah, okay. So if we have the pion with momentum p, this will be up, this will be u bar p. This gives q, it's the current, and this is the p meson. So if one calculates this diagram at leading order, which is very simple, then one gets this expression. So maybe it's not so clear, but I'll have to give you a reference to see how it's done in more detail. Okay, so this is the leading result, and as you see, it's very simple, and we can rewrite it like in this form. Okay. Yeah, okay, the definition of the, you wanted the definition of the light cone distribution amplitude, and I didn't do it to you earlier, so I'm going to do it to you now. It's simply like this. IP, U, 0, 5. This is a Wilson band between 0.0 and x to make the engaged invariant, and 0. And that is equal to minus I f pi p mu 0 to 1 p mu e to the I u bar p dot x phi mu. So this is the definition of the light cone distribution amplitude, and you see that it comes along with this f pi, the pion decay constant, which is why the f pi enters here. Okay. Okay, so where are we? We have an expression at leading order from the light cone expansion of this pi plus in terms of this light cone distribution amplitude. And on the other hand, we have an expression in a hadronic expression in terms of FB, F plus the form factor, and some spectral density, a hadronic spectral density. Yeah, I'll share references for the form factor soon. So then what do we want to do? We want to equate these two expressions. And further, we want to assume something called Cochandran duality, which is not a precise assumption. But we say that above some momenta q squared, which we call S0, that the Quark representation is the same as the rho T2. So we can subtract it from both sides, and in the end we just have and we have FB and B squared F plus FB squared over MB squared minus PB squared is equal to what? Just this from 0 to S naught, 0 to 2 over S minus PB squared. So assuming for duality. So that means that we'll have equals rho T2 with the theta function S minus S0. So this S0 is called the continuum threshold. Okay, so because this assumption introduces this a new number, a new constant S0, and because it's not an exact assumption, then what we do is we apply something called the Boreal Transformation, which is something that suppresses the contribution of higher Q squared. So it should make this Cochandran duality assumption less important, but at the same time it introduces a new constant which we also don't know. So in the end we have two constants that we don't know. So this Boreal transformation looks like this. And so in the end we get an expression for F plus, which is like this. Okay. So this is the leading in alpha S and the leading twist contribution to the form factor from light consummers. As you see, it takes a simple form, but as I mentioned, there are two constants that we need to determine, and that there are some fixed procedures which we use in order to determine that. For example, if we differentiate this form factor y 1 over m squared, the Boreal parameter, then we turn out to get a sum rule for the mass of the B meson, MB. So we can say that we must satisfy this sum rule to a very high degree, and that fixes one of our parameters. The other parameter can be fixed by insisting that the sum rule is stable, by insisting that the contributions of higher twists are under control so that the sum rule converges. One can make several kind of physical constraints on what the sum rule should look like, and that helps you get some idea about what the parameters should be, and then afterwards you assign large errors to these parameters, and that should give you a reasonable estimate of what the form factor is. Does anyone have any questions?
Yeah, can you shortly explain like what is leading twist and like twist N?
Yeah. So I mean, the easiest way, there is a definition of twist, but I don't find it very insightful. Basically, I would say that the leading twist is this phi where you just have two constituents in the electron distribution amplitude. So you don't assume any extra partons in the pi meson. You just assume that it consists of the valence partons. And then you can increase the number of constituents. And the other thing that one needs to know is that once you go to higher twist, then the contributions are suppressed by factors of roughly 1 over E, where E is the energy of the final state meson. So the fact that this electron expansion works like that, the higher twist contributions are suppressed by this 1 over E, means that it's basically, you need to have large E. So it's more or less, it works more or less at low Q squared. So like when someone gives results which are valid at low Q squared.
Okay, I see. So low Q square, is it related to like light cone distribution? So because Q square is like small.
The light cone expansion is always.
Mm-hmm.
Yeah.
Okay. Yes. Thanks.
So is it low Q square or high Q square? Because light from someone who takes the high words like large Q square in the equilibrium, right?
No, large energy and low Q square.
But for B physics, right? For other thing, it's high Q square. It gives for high Q square.
So the light cone dominance requires Q square to be very large, right?
The expansion about this point x equals 0 requires Q squared to be small. PB squared minus M squared, MB squared is large and negative.
So your Q square is basically a momentum transfer, right?
It's a momentum transfer, yeah.
Yeah, so I'm a bit confused here. So as far as I read, light cone dominance requires large Q square.
No, that's not true. So yeah, I can one very nice set of notes where this is explained in detail. I'll just get it.
Q is the 4
there's-
momentum, right? So Q square large means the mass is small compared to the energy and the momentum. So the momentum is nearly equal to the energy. Yeah.
Yeah, there's some notes by Colangelo and Cochandran, QCD Summers and Modern Perspective. And there this is explained in detail. There's not many places where this is explained, but here it's explained well. I put it in the chat. So I think Anshika, if you read that, I think it will be clear. And maybe if it's not clear, you can ask me tomorrow.
Yeah, sure. I'll just read it once and then.
Okay, great. Any more questions?
Aoife, maybe I have a slightly a provocative one about how does this work in the charm sector, and what are the additional problems that are there?
Yeah, I mean, so I haven't. I would like to work on this more in the charm sector. For the moment, I haven't really worked on microensembles for the charm sector, but I guess in the charm sector, the problem is that just that the scale is not so, the scale MB is not so high. So anywhere where here we're using the fact that MB is large, it works a bit less well. And the other thing, well, yeah, and then I mean the fact that alpha S is larger. Yeah, because normally one takes a scale for these calculations, which is kind of below MB. And so for the charm case, you take it even lower. One sec, let me just check what we normally take for the scale. Yeah. And so the typical scale that we take for factorization is the square root of MB squared meson minus NB squared quark. The factorization scale is NB squared minus NB squared. And I'm guessing for the charm case, this is quite small for perturbative alpha S, but you can do it.
Yeah, I just know that it's a lot more difficult, and I guess you have to maybe go to higher orders or whatever to
get a more reliable result.
Yeah.
But I mean, it's been done, right? I mean, Alex Kojamian has worked. I mean, Patricia, my supervisor, also had some results for D mesons, and Alex Kojamian has quite a few results for D-pi decays. I mean, it's very simple for us to do it because we just change a few. Parameters, and then we've got the result. The other problem, of course, is that these light cone distribution amplitudes are less well known for the decays. But if the final states are the same, then in this set of light cone ensembles, it shouldn't matter. So sometimes people have another form of the light cone ensemble where it depends on the initial state light cone distribution amplitude rather than the final state light cone distribution amplitude, and I know that the B meson is known better than the D meson, but the pi meson is known better than any of that. So for D to pi, that shouldn't be a problem. Yeah.
Okay, that's it. Thank you.
No. Any more questions? Okay, great. So, okay, talking about this Q square is exactly what I was about to come to. So we see from here that the form factor is a function of Q squared, which will be in here and here. So what we really need is some parameterization of the form factor in the whole range of Q squared, which is measured. And as I said before, the electron sum rule is only accurate at low Q squared. And on the other hand, the lattice QCD results best at high Q squared. So ideally, we need some sort of parameterization of the form factors, which give you some result over the full Q square range, which you can fit to the LCSR and the LQCD results. And why the lattice? Does anyone know why the lattice QCD results are accurate at high Q squared? Yeah, it's because the final state meson, they want the final state meson in order to simulate it on the lattice. They want it to not be energetic. So, so that apparently if it's energetic, then that creates some noise on the lattice. Okay, so in order to design some sort of parameterization, one thing that we can take into account that the form factor is somehow, the shape of the form factor is affected by low-lying resonances that appear just beyond the physical range. So we have a form factor, for example, like this. And imagine that the B and the U could form a resonance. So there's the B star resonance, and this affects the shape of the form factor. So these need to be taken into account when designing some parameterization. So the low-lying resonances should have the right quantum numbers for a given form factor. And similarly, one can check, yeah, for all of the form vectors, what low-lying resonances there might be. Yeah. So, I mean, a very basic parameterization would be something like F0 over 1 minus Q squared over MR squared, but MR is the mass of this low-lying resonance. But this might be a little bit too basic to fit the form factor, so you might need something with a bit more degrees of freedom, something like 1 over Q squared over MR squared plus F2 1 minus Q squared over MX squared. something like that. So these we call kind of simple pole or double pole parameterizations. And however, this sort of parameterization has gone out of fashion, and nowadays most people use something called series parameterizations. And I think I'm going to just talk about those tomorrow morning before I talk a little bit about QCD factorization. So why are these series parameterizations popular? It's because by using some theoretical input, there's a way of putting a bound on the coefficients of the series. And this allows you to have some theoretical information that helps you know what the form factor shape should look like. And bounds, well, how much error comes from the fact that we don't know the shape of the form factor. Okay. Julie asked, can you give idea about power corrections? Of what? What power corrections?
Ma'am, power corrections of form factor.
So the two types of corrections. One is you can go to higher orders in alpha S when you're calculating these Heart Kernels T. And the other thing is to go to higher twists. So for the F plus, for example, we have gone up to twist 4 at order alpha S, and twist and 5 and 6 are also known, and they're very suppressed. But up to twist 4, it's substantial. We also know for twist 2, we've gone up to order a part of the order alpha S squared corrections. And those results are also quite small. It's a 10% effect. So going up to order alpha S squared. So no, it's not a 10% effect. It's smaller than that. Sorry, it's more like a 2% effect. So so I think that now for beam meson decays to a single meson, everything is known that that we want to know for these light ensemble form factors, more or less, because there's an inherent 10% uncertainty coming from the fact that we don't know this continuum threshold and this Boreal parameter, and so there's no point calculating further corrections because we're already at this 10% level and we can't get below it. Is that what you meant, Julie? Yeah. Does anyone else have any questions? Okay.
I don't see any more coming in.
Yeah.
So thank you very much, Aoife, and we will see you again tomorrow morning. And in the afternoon, I believe, as well.
Yeah.
Because,
yeah.
So the tutorial. So everyone should take a look at the tutorial problems that were circulated yesterday, I think, or the day before. I can't remember now. And whatever questions you have, we covered tomorrow.
Yeah.
So yeah, thank you very much.
Okay, thanks to you. Thanks to everyone for your questions, and see you tomorrow.
Thank you. Bye-bye.
Bye.
So
Bye. Bye.
So thank you, everybody. We'll start again at 10:30 tomorrow morning with Diego's last lecture. All right. Thank you. Good night. Bye-bye.